Okay, we're talking about implicit differentiation today, but before we do that, let's talk about what explicit differentiation is. So, explicit differentiation, or an explicit function, I should say, I really should say a function that's explicit. So, let's say explicit functions are those functions that are like clearly defined. So we've been working with those like all throughout algebra, and into like algebra 2, into pre-cal, college algebra, things like that. Suppose you have the function, I don't know, x cubed plus 2x squared plus 5x minus 4. This is an explicit function, clearly defined. It's got its own dependent variable, and it's got independent variables in terms of x. Okay, so this is an explicit function. When you have what's called an implicit function, and that's what we're talking about today, this is something where you might have something like xy plus 2xy squared equals 4. Okay, notice the difference. Over here, y was its little dependent variable right by itself. Here, y is not easily separated. Okay, sometimes it can be separated and you could take a derivative, but not always. And so that's why we have the need to study functions implicitly. We're analyzing implicit functions, and we're doing that by taking implicit derivatives. So what we're going to do is we're going to look at this in terms of taking the derivative in a couple of different ways. And what I tell my students is that when we do, suppose d dx of some function, okay, I call this, all right, the x treatment. I call it the x treatment. But then when we take the derivative with respect to the variable y of the same function, okay, and it actually should, in this case, should be something like this, f of x comma y. Okay, I call this taking the y treatment. Okay, so what we're going to do is we're going to take a look at this first problem, 2xy. I'm going to rewrite it, 2xy minus y squared equals 1. And I'm going to take first, or apply, the x treatment. Okay, the x treatment. So what that means is I'm going to take the derivative with considering x as the variable, and if there's a y, we're going to treat it as a constant. So if I look at this right here, I have 2xy, okay? My variable there is x, okay? So what that's going to do is I'm going to take the derivative with respect to x, and I'm going to be left with 2y. 2y, because I dropped the x. It's a linear combination there. Now this y squared, all right, you take the derivative with respect to x, but it's not, it doesn't have an x. So what we say here then is that this one right here is treated as a constant, and the derivative is 0. And the derivative of 1, of course, whether you're taking the derivative with respect to x or y, the derivative of 1 is 0. It's a constant as well. So now we go in and we're going to apply the y treatment. Okay, so that means take the derivative of the whole thing again, but now with respect to y. So what we've got here is we've got 2xy. So now the variable here is y, and I'm going to say, so plus, okay, because it's positive, 2x. All right, but because I took the derivative of a y, I have to state that I've taken the derivative with respect to y, and I'm going to write y prime. Now sometimes some teachers will say, well, write dy dx, but I write y prime. It's just easier to keep track of. Okay, now Here, we take the derivative with respect to y of the negative y squared. So we're going to have negative. Now, y squared derivative is just like an x derivative. If it was x squared, we'd say 2x. But in this case, it's a y squared, so we're going to say 2y. And it's, again, negative. So we say 2y, but then we have to say y prime, because we took the derivative in this case with respect to y. We have to state that. Okay? And now we take the derivative of 1 again, and the derivative, whether it's x or y one more time, it's a constant, so the derivative is 0. And now what we're going to do is we are trying to find over here dy dx, but for us that's the equivalent of saying we'll find y prime. Well, I've got my y prime right here and right here, so my job is going to be to isolate that variable there. So what I'm first going to do is I'm going to move this to the other side, and then I'm going to factor out the y prime that's here and that's here. So I need you to follow along and see what's going on here. So first thing I'm going to do is write my y prime on the outside. On the inside, I'm going to write 2x minus 2y, and then equal negative 2y. So if you notice there, the 2y got moved over to the other side, just like that, and the y prime was factored out. Okay? So what do I have? I have y prime equal to, now I'm going to divide by this on the other side, negative 2y divided by 2x minus 2y. And I've basically solved for y prime. Now what I can do here is I can actually factor out a negative 2 or a 2. All right, I'm going to factor out negative 2. That'll make my numerator positive, and that's actually kind of nice. So y, so I'm dividing out negative 2. And then I divide this, so this got divided by negative 2, this gets divided by negative 2, this gets divided by negative 2. So I can change up the order just a little bit. That's going to give me a positive y and a minus x. Okay, so this right here is my y prime, what I'm looking for, which is the derivative of that implicit function. And so if we were to ask you what's the slope of the tangent at a particular point, well, you'd plug in x and y into these variables here. Okay, you'd plug in x and y, you'd have to plug in both, and that would give you the slope of the tangent for that implicit function. So it's actually kind of neat. So rewatch this if you have to, but let's take a look at another example. Okay. This next one is actually kind of a fun example because it involves a trig function, and trig is always fun, at least in my eyes. So, well, you're probably also thinking that I need to find a new definition of fun, but anyway, I digress. Sorry for going off on a tangent there. Yes, that was a calculus pun, but let's go ahead and take a look at this one. The cosine of xy plus x cubed equals y cubed. So what we're going to do is do the x treatment first, take the derivative with respect to x, and then we'll take the derivative with respect to y, and then put all this good stuff together. So first with respect to x, well, I've got the derivative of cosine, which is going to be a negative sign. So I'm going to say negative sine of xy. Okay, now because of the chain rule, I've got to multiply by the derivative of the inside. So the derivative of the inside of xy, you're taking the derivative with respect to x, the derivative, then you're just left with y. So you have to multiply this by y. Not y prime, just y by itself. Okay, then we take the derivative one more time, and now we're looking at the derivative with respect to x, but of x cubed. So that's 3x squared. Okay. Now we take a look at the derivative with respect to y. I'm sorry. Well, you take the derivative of the right-hand side of the equation y cubed, and that's going to be 0 because you're looking at it with respect to x. Now we go ahead and do the same thing, but in this case with respect to y. So it's going to be almost the same. Okay? So you're still going to have a minus sign because you take the derivative of cosine, you still have negative sign of xy. But in this case, when you take the derivative with respect to y, you're left with just x. So you're going to multiply by x, but then you also have to say y prime because you took the derivative of a y value, or of a y variable. Okay? Now, you take a look at x cubed, derivative of that with respect to y, that's just 0 because it has no y, so we treat it as a constant. So now we're ready to write our equal sign, and now we take a look at the right-hand side of the equation. We take a derivative with respect to y, and that's just going to be 3y squared, just a regular power rule. But we have to say y prime. So we did on this side here what I called the x treatment, meaning we consider x as the variable, and on this side and this side we did the y treatment, okay, considering y as the variable. Okay, now our goal is going to be to isolate the y primes. So there's a y prime and there's a y prime. So the trick is get your y primes all on one side. So let's go ahead and do that. What we're going to do is we're going to move this guy this way so that the y prime's over there. And all of this stuff that was on the x treatment, we can move this way. Okay? So it's just going to kind of swap places, all of that stuff. So we're going to do that. And let's see what it looks like here. Suppose I have negative 3y squared y prime minus the sine of xy times x y prime. Set it equal to a positive sign, because when that sign goes to the other side, okay, it becomes positive. Sine xy times y, all right, minus 3x squared. It looks something like that. Now, notice I'm taking a lot of steps for granted, but you really just need to visualize it, okay? You don't have the time anymore to be doing, little minor steps. Next thing we do, we notice we've got the y prime, and I probably should have done it already, but, we're progressing. Negative 3y squared minus sine of xy times x, and then I factored out the y prime, and it's still equal to the same stuff that was over here. Same stuff. Okay. The only thing I'm probably going to do is put that variable in the front, and that's about it. Okay. But other than that, I'm going to now divide by this on the other side. So let's just do it already. Move the x in the front. Okay, just like that. And divide it on both sides. Okay. And so, let's move this page just a little bit. I have my y prime equal to, and I'm going to say y sine of xy minus 3x squared divided by negative 3y squared minus x times the sine of xy, something like that. Okay, and that's not too bad. I mean, the only other thing I could do, maybe I could probably factor out a negative 1 and make the 3's positive, so I don't have that kind of negative oddball in the bottom. But this is pretty good. So let me just go ahead and factor out that negative 1. So basically we're dividing everything by negative 1. So it's going to give me a positive 3x squared and then a minus y sine of xy, something like that. And then it's going to give me a positive 3y squared and a positive x sine of xy. Okay, so this right here will be our y prime, our dy dx. Okay, again, nothing more to do here other than state that this is the derivative or the function of the derivative of this implicit function. Of course, if you were asked, to find the slope of a tangent, you'd need to be given some kind of point x1, y1, and then you'd plug in those values in for x and y, and whatever number you get is the slope of the tangent. You could, find the equation of a tangent line and all sorts of stuff like that, but we'll save that for another problem in probably just a few minutes. So, I know this video may have been long-winded, but watch it again if you need to. I hope it was helpful, and as always, like and subscribe.